And then a series of postdocs here and there, Potsdam, Portsmouth, Heidelberg. Where else were you? A lot of places. Vienna, and now he's a permanent staff scientist at Bošković Institute in Zagreb. So there you go.
Of course, very important side note. She was my PhD supervisor, advisor.
That's why he's here.
Did forget that, yeah.
I forget that sometimes.
So, okay, so I prepared a talk today, which is potentially a bit off-grid from your normal work, I assume. Yeah? So I've given all talks here beforehand. So I gave a very heavy overload of introductory slides. But of course, if there's anything unclear, which probably there is something accidentally in there which you probably get confused with, just interrupt me anytime. So today I will talk a bit about like some new developments, basically how we can predict the cosmic structures. So here, for example, you see like a light cone. So this is actually a simulation result here. So from our new simulations, where you can basically with our new techniques, you can basically directly initialize our simulations at the Big Bang time, and this makes things easier in usage later on. And why are we doing this at all? So first of all, when we look at the observations of like on a very large scales in the universe, like these points here are basically just like clusters of galaxies, and there's kind of filamentary network. And that includes the distribution. This contains a lot of information that we want to assess. Information about inflation, information about parameters used, and so on. And to infer all this, we only have a single realization, but we need to somehow infer these parameters that are unknown a priori. We need to run a lot of simulations. And of course, every simulation needs to fix parameters. So need to have a lot of simulations to get like a big sample of settings or parameters, and then you try to basically infer like the unknown parameters from that. And unfortunately, running these simulations is very costly. I mean, you have billions and billions of particles basically. And so one very important point of this talk is how can we basically make something that is extremely costly more efficient without really scrutinizing the accuracy. Yeah? So, and this is possible actually. Yeah? And the good thing is, because I mean, this is not really completely my background. I mean, past years, my main topic is actually perturbation theory. Yeah? So it's maybe the opposite side. If you do cosmology, you do either like simulations or perturbation theory. Yeah? But in the last few years, in particular with this guy here, Oliver, but also with his postdoc, we worked a lot on trying to close this gap. And actually, so what I'll show you today is essentially like exploiting like really insights that we gained from perturbation theory to make simulations much more better than before. Yeah? So it's a good thing because part of physics or whatever you do in practice, you know perturbation theory. So what I'm doing here is actually not that different from this perspective. Okay, just a quick picture. So the basic framework is we do Big Bang cosmology, which we assume that there is the Big Bang in an inflationary phase, accelerated expansion of the universe. So so you probably have seen this before. What is more interesting is actually the later phases, because for us this is just a tiny fraction of a second, but 30 million years of time. This is where it becomes information rich, I would say. I mean, the early phase, the plasma phase, where basically the whole universe was just a soup of primordial particles, mostly baryons, electrons, and photons. And because of a nice interplay between different forces involved, that basically is just wobbling a bit around in space-time, doing some oscillations. So small fluctuations around the linear solution, basically, which is quite nice. Basically, it means that we can just use like a linearized system of equations at these early times and get a very nice prediction from it. Then it gets more complicated later times, because once essentially the universe expands more and more and the mean temperature drops, which means some interactions freeze out. And once the interactions become ineffective, particularly like the electroweak interactions, you basically have a freeze out of them, and then matter can cluster almost freely and matter or gravitational interactions are highly nonlinear, so things get very nonlinear very quickly. Yeah? And the system is described by a set of collisionist-Boltzmann equations that I will just also quickly review. So the main starting point when you look on the larger scales in the universe is that you need to work with an effective description. Effective in the sense is that we do not implement, most of us at least, like particle microscopic effects. Why? Because we have actually good observational data telling that this is on these large scales is not relevant. I mean, you basically try to first work on the leading problem, like the book problem, and once you have understood that, which is really quite difficult, you try to incorporate like these little perturbations around it. So we can actually use for many of like deviations from what I'm saying today also with perturbation theory. But the main problem is really just this, that we have like a dark matter fluid that behaves collisionless, and this is this kind of fluid is described by these Vlasov-Poisson equations, which actually look probably for people who work on like field theory methods with Boltzmann equations and so on might look very boring because you have no collision term here. But exactly opposite is the case in my opinion, because if you have collisions here on the Boltzmann equation, you have something that can avoid like some severe actions basically, right? So if you have like, for example, some photon interactions on this side here, you have like a counterforce to some extent that prohibits like very strong fluctuations. Here you have nothing that prevents you like a really like strong nonlinearity. So the system here is extremely complicated to solve. So even like doing numerical simulations, the problem is actually quite tricky. It's quite dry area, isn't it? So, okay. So, and another very important bottom line or conclusions from a host of observations is that dark matter seems to be extremely cold. Cold meaning that I mean, temperature is basically 0 Kelvin. This is what we assume in this kind of starting point of the model. And if you look in phase space, we can show here position over velocity and over time. That this that the whole diameter distribution or the function of it is just encapsulated by this kind of manifold. So this is infinitesimally thin. So what will happen because of gravitational interaction is that this fold, this shield will fold in due time because of interactions, yeah. But it will always remain with this kind of support in this in the vertical direction because of this initial coldness of the diameter sheet. And yeah, so also here you could in principle ask the question why don't we include any thermal effects? We could, but it's by far not the leading correction to that. So this is, we have more problems that are much more vicious and much more dominant than like thermal residuals from the sheet. So many techniques to calculate the evolution of dark matter on these large scales use a very, it's an optimal parameterization basically of the problem. And for people who didn't work on fluid mechanics, you basically do fluid mechanics on large scales with that. And what does it mean is that we actually use Lagrangian coordinates, which are really just name tags. You think about like a fluid, any kind of fluid can be water or whatever, so you just tag them with some label. And the label is just a coordinate basically, yeah. And then you just let time go, and you follow these kind of fluid labels. And in a sense, if you have an equation that describes the fluid system, you add a parameterization to these fluid equations. And this is exactly what's encapsulated in this kind of shorthand notation here. So it might make superficially things more complicated looking, but it's actually opposite. Yeah, it's actually quite it gets simplified, as you will see in a second. And just for people who have no experience with fluid mechanics, when you think about Eulerian coordinates, it's just like a fixed coordinate system where you have like somebody sitting here on the side and just observing the fluid stream here. And the Lagrangian coordinate system is basically that you're sitting on this boat and you just follow the fluid flow. And you do this not just for one fluid particle, but basically for all. Which sounds complicated, but it really isn't, because it's really just a label that you follow for all fluid labels. So the crucial point about any progress in this highly complex problem is the right choice of coordinates. So there's like a one-to-one correspondence between all these coordinate systems, but for the problem at hand, it's just dark matter evolution. All techniques are, I'd say 99% of techniques that we use are using Lagrangian coordinates in simulation techniques, but also perturbation theory. Why? Because it is the optimal choice for the current problem. But if you have one solution, you can of course also project it to the outer space and back and forth. So in principle, the different spaces are linked to each other at all times. But the question is, which one is the more accurate description to keep errors under control?
I have a question, if you don't mind.
Sure, yeah.
So is there a reason why your initial condition is chosen to be some cos function with a cos inside, or is it just...
This is just a toy model. This is really just to encapsulate this kind of... I mean, what we know is that at CMB times, that the initial velocity should be single valued, which means that you at all locations in space, you just have velocity, and you have potentially a velocity dispersion, but it's highly suppressed at that time already. So it's really just like a single valued velocity field, and this is just a simple toy model that I'm showing here. This is not the actual simulation.
Yeah, that's fine. Yeah, absolutely.
Yeah. So I'm showing such simplified figures quite all the time, because in the universe, our initial conditions are random nature, so they are like Gaussian. So you have, well, you know, if you expand locally like a Gaussian field, it may look like something like cosine, but if you zoom out, it looks much more complicated, of course. So excuse me, I think the air is really dry here when I talk. Somehow it dries up. So the nice thing about when you work in Lagrangian cons is the following: that you have actually a simplified system of equations. So this is just a Newtonian type of equation, where you have the acceleration of particles is basically equal to the gravitational force. So it's a simple equation by the looks of it, and the problem is really simplified. Why I'm saying this is the following: whenever you work with a complicated problem, you first need to reduce the problem in an essential way, because if you work on the level of Vlasov, it's really complicated. But if you really deduce basically that this system of equations is identical to that one, you have made already the first big step. And why is this identical? Because we assume in the first step that the initial conditions are of cold matter is cold, extremely cold. So all thermal components are not implemented in this description here by nature. But this is only like...
Isn't that just the matter of initial conditions?
Yeah. So you can only do that trick here, of course, because you use cold initial conditions. But this is valid at all times after that.
That's true all the time, right? Isn't it?
No, you can't. I mean, how can you incorporate the velocity dispersion? I mean, you will.
I can.
You will incorporate it. No. But x is really just like the initial velocity. So if you want to incorporate like a velocity dispersion, you can, but it will be basically driven by this kind of sheet falling. So here, for example, at this point here, you will have like 3 velocity streams. So you have like effectively a velocity dispersion tensor at this point. But here in this time, in this early slice, you have just 0 velocity dispersion and so on. So you do, of course, generate velocity dispersion, but really just because of the onboarding evolution gravitationally. Yeah? But it's not included in the initial conditions, because this is the starting point of basically all techniques that we use in cosmology at these large scales. So be it perturbation theory or embodied simulation techniques, this is what you basically do here. Unless you want to really include like particle properties. So the system is still quite complicated to solve. Why? Because of this collapsing feature. So if you have like a potential and you just let the particles let their way, they will accumulate at this very focused locations. And the density, the matter density can go very large, I mean extremely large. I'll show you this also in a second. One of the key problem in our theoretical point of view was actually to investigate what happens when when essentially this collapse happens the first time. The first time we call it actually it's called shell crossing, and this is again just like a simplified picture of it. This is just a one-dimensional toy example. You have like only one space dimension, and you have initially just like some trajectories of dark matter, and they also have this kind of folding nature here. So they tend to go next to each other. And you have this point where they intersect the first time, and this point is called shell crossing. And this point is very important because in the matter of phase space, basically we move from a distribution that was single stream, which means no velocity dispersion, into regime where you have non-zero velocity dispersion. That's what I'm just trying to say before, that you now have like because of the collapse of the structure, you have basically diameter particles going this way, and then they start oscillating around each other. Yeah. Okay, that's what's happening in this region here.
Again, can I ask a stupid question? So, which is the fact that you have, and maybe you mentioned this and I didn't quite understand. So, the fact that you have a non-zero velocity dispersion is simply gravitational interaction and nothing else.
Yes, exactly. Yeah.
And because you're effectively generating an acceleration, right? I mean, that's what's happening.
Well, you have a collisionless fluid, and collisionless means that there's no counterforce, and then basically you have the particles that just are on the same location at the same time.
Right. Yeah.
Exactly. Yeah. So again, you could in principle also include like other sources of velocity dispersion. But this is what most people don't do, yeah, because the Wolf problem is really in understanding this already, which is very complicated already.
Yeah.
Okay.
But again, so, can I go back again? So, but what kind of dispersion you generate should be dependent on the initial conditions?
Can you rephrase the questions? I didn't really understand.
What kind of dispersion you generate should depend on the initial conditions.
Sure, yeah. But we have good understanding of how that looks. We can actually also extract velocity dispersion from simulations, for example, and it's just a matter of initial conditions. So we know at least statistically it should be very close to like a Gaussian, the initial conditions of our problem. So, for example, you will also not just have like one location where you have shell crossing, you have basically lots of locations somewhere in space where the first time the metal streams are overlapping the first time. So yeah.
Because
so
eventually you're going to do this for a 3D realistic simulation where you have to match structures with whatever initial condition you set up in some sense.
Yeah, sure, yeah. And it is already, yeah. So what I'm showing here is really just a pedagogical overview, basically, yeah. So we actually have an understanding of this process in full 3D, even for like realistic initial conditions.
Yep. Okay.
Yeah.
All right. Thanks. Yep.
Yeah, I'll come to this actually in a second, I think. Yeah. So just quickly to understand also, if you still have not enough intuition about Lagrangian coordinates, when you look here on the right-hand side, these kind of different color schemes is really just like, think about again a fluid, and you just basically colored like the fluid particles before you press start. And you see basically that the initial velocity, I mean, again, this is just a toy model here on the right-hand side. You see that it's just like a cosine initially, or sinus, sorry. And you see that the particles basically are moving slightly towards this center area here. And the point, which is here shown here as shell crossing, is exactly the point here in the central panel. You see it looks pretty harmless here in the velocity over x space. But when you basically do the math, you see actually that when the tangent here of this distribution function is exactly vertical, there's like a derivative basically that dictates you that the density has to go to infinity here. It's just a matter of mass conservation, basically. It's just these equations underneath, they just tell you the mass has to be conserved at all times because you don't have any kind of collisions, right? So, and locally, if the phase space gets so deformed, basically, that the tangent is vertical in this one-dimensional problem, you see that the density goes to infinity. Yeah? So this is quite a vicious problem in principle. But it has been understood that this is not a problem for simulations, either for perturbation theory, for example. So we can actually investigate this process here to extremely high precision in both simulations or by analytical means nowadays. But this is only thanks to a lot of progress that happened in the last 10 years roughly. And very important for people who have problems with singularities, these are singularities we really have control of. They don't point towards a problem to the underlying description. We can actually really handle them in an accurate way. Yeah.
And how sensitive is it to, like, let's say I want to put some ad hoc regulator that's saying that, like, when the density is larger than this, then the approximation of a neglected equation, for instance, is not good enough. How sensitive is it to, like, I don't know, the size of this kind of regulator? I don't know.
Oh, you can do that. I mean, in practice, also lots of simulation techniques actually do incorporate such a regulator on small scales, but for numerical reasons. But yes, sure, yeah. I mean, in simulations, you basically try to include such a regulator to not excite like unphysical residuals, but in principle, you can also use this to incorporate physical knowledge, like particle physics, for example.
And that changes the dynamics
a lot. I mean, there's not so much literature on this. I'm aware of people who attempted to do these simulations for primordial black holes, for example. And there you want to include some of these interactions in small scales, but it's I don't think it ever got published. So it's still early days to do that stuff. So right now, the most focus is really to understand the heart, the core problem of that. And once you have really control of the numerical errors, so even if a simulation is extremely accurate, this is highly complicated to calculate. And then you might think, okay, let's add a regulator to make this more easy, possibly. But I think it's more like a bottom-up approach. You will want to first understand the core problem, and once you have that, you go like include the other stuff that may make it easier. But if you do it the opposite way, this is at least a feeling of the community, as my feeling as well, is you should first start with the tough problem and then go to the slightly easier one. I mean, including particle physics might actually make this problem easier here for us. Yeah. But also, we don't know what particle physics model we should use. I mean, I don't really like primordial black holes, for example, and axial particles. I don't think this is really feasible. And then you would use a different simulation technique here, for example. So I mean. So I'm using here in this talk, if you have interest, we can talk about this later. I work on this too, on Schrödinger-Poisson simulation techniques. Schrödinger, basically, this is completely off topic here, but there's a correspondence between Vlasov-Poisson and Schrödinger-Poisson. You can basically find like a quantum analogy between these descriptions. And then you can also include particle physics in this kind of Schrödinger-Poisson description. But it's a different thing. It's not exactly the same what we're doing here, but we can talk about it. Okay, just speed up a bit. There has been some progress on what we can do about these shark crossings. Let's never mind these details. I mean, we can talk about this later. It's just I mean, to understand this highly complicated problem, we had to basically first start with simplified initial conditions. And once we had a good understanding what we can do with derivation theory, we switched on all the details as good as possible. So by now we actually can calculate this moment of shell crossing to a very high precision, really by analytical means. Analytical in the sense that we still need to use some kind of numerical approach. Why? Because the initial conditions are Gaussian in nature. So basically, you calculate things for Gaussian initial conditions. You need to sample it somehow on grid points. This is just so there's numerical calculations included here as well. This is not yet a simulation we're showing here. For example, this is mostly like theory prediction, except the black dot lines here. Yeah, but still, we made quite some big progress to understand this first instance here. But all these techniques that you see here, for example, or also these results that we found, or others, it's very important to have the right choice of coordinates. If you have the wrong coordinates, actually last year I gave a talk here as well. I gave you an example of what happens if you have bad choice coordinates. But I will not show this again. If you want to talk about it, can talk about it soon. Let's talk about the right choice of coordinates, at least for this problem. If you just really care about large scale structure of universe and you only have essentially dark matter, dark energy, Lagrangian coordinates is the way to go. Why? Because the whole problem is just advecting essentially fluid particles. And advection problem is extremely efficient to do in Lagrangian coordinates. And And the equation of motion actually looks, it is just not look, it is identical to the one that also numerical embodied simulations are solving. It's just the details that decide what is then at the end a theory approach and a numerical approach. For example, here you have like a second order differential equation. So and it's solved by like a force term. And in a sense, perturbation theory and simulation techniques, they use two different approximations. When the perturbation theory basically is time integrating this approach here directly by an appropriate ansatz, whereas simulation techniques basically they use digitization of these time derivatives here. And of course, this calculation of the force term is different in simulations. I will come to this also in a second. Yeah. So in perturbation theory, the force is basically calculated as like a perturbative feedback. So it's like self-feeded in a bootstrapping mechanism, and it's quite easy to solve by like an appropriate ansatz. So what you do is basically in these kind of frameworks, you assume that you have like a homogeneous contribution basically, and you start expanding around like a certain smallness parameter, and then you go to higher orders and orders. And we have by now actually calculated these things to extremely high order. I mean, why? Because at least once we had to make sure that the series actually converges, right? Because we wanted to really show that it's not just an asymptotic prediction, but really like a convergent prediction what we have here. So basically we calculated this kind of series up to 40th order, which is extremely high. I mean, just as a comparison, if we won, I think 12 years ago or so, we did a calculation to 4th order, and this is now 40th order. This is a completely different story. And it's also not recommended to go to 40th order. It's really just to understand once that the series is converging, you need to go to very high orders to make sure that the problem is well behaved. Okay, let's talk about simulation techniques. So this is the main part of the talk today. So first of all, there are a couple of approximations. Even if the simulation is completely looking brute force and highly accurate, there's always approximations involved. And one of the most commonly used technique actually, it's not just going back to these papers here, which are cosmology papers, but it's actually discovered or like has been first used these techniques in plasma physics. Why? Because in plasma physics you have actually very similar problems that what we have in cosmology. Yeah, it's actually very similar description of equations you have there. Yeah? So the first very important approximation is that most techniques use the so-called embodied method, which means that you assume that your distribution function is indeed like continuous, but you just try to basically co-sample the distribution function at collocation points. Okay, so you can think about this here as shown on the right with this figure. So ideally you use as many particles as you have, but it's extremely rich in information, and if you more particles necessitate also much more requirement computationally. Huh? And the particles that we use nowadays with supercomputers, they go like in the range to 12,000 cube particles. It's a lot of particles actually, but honestly still not far enough basically to really go from all the scales interested later on. And when you just do the math, basically what is the mass of these tracer particles, you're far away from like actual dark matter candidates. So again, this is these dark matter mass and the particle mass of your tracer particles have nothing to do with each other. Why? Because it's really just a co-sampling, and you actually want rather reduce like interactions between these end particles, because this is not physical unless you really show me like a candidate that has such a big mass, yeah? Like maybe a brown black hole, yeah, for example. Yeah. And the next step is that you need to somehow time integrate the equations, because you have second order differential equations. And one of the base approach to deal with this in cosmology, but in many other problems, is using a Hamiltonian approach, where you basically assume a symplectic integrating scheme, where you do the first trick that goes back to many, many years ago. Of course, you split a second order differential equation into two first ones, and then you basically do this in a clever way so that the coordinates that you want to solve here are canonically conjugated. Why are you doing that? Because when you do it in a symplectic or canonical way, there are some certain conditions satisfied built in your system, like incompressibility of Liouville theorem, if you know statistical physics and stuff like that. So this is very nice built-in features you can have here. And in practice, you do not time integrate these equations by just integrating these equations, but you do this in a discretized way. And you do this often in this kind of a building block form like this. So what you do is you basically do one time step, which is not epsilon, of course, but it's a little larger maybe, yeah. And you do usually 3 operations. You first form a drift, so really just like drifting particles, falling like they had some initial coordinate, and then you give them like another momentum, and you just basically displace particles according to this momentum here. And you do this for all the particles. This is should maybe add here labels of particles as well here. And once you do that, you basically do the same for also something very similar for the momentum. You give also an update for momentum, which is a function of the previous momentum of the previous time step, and also of the acceleration that you calculate by some method that I will also explain in a second. And then you repeat this again for the drift part, and then you basically have a completed time step. And you will, of course, do this for lots of time steps. I mean, thousands of time steps for a normal simulation. And the good thing is that by splitting this up in this kind of symmetric form, you have certain energy conservation built in your system. So you have like second order accurate scheme global, just because you do this kind of drift, kick, drift. You can also do kick, drift, kick, for example. This is, has very similar properties. So it uses certain errors in your integrating scheme. This is always a good thing to do. The next thing is, this was one kind of approximation, discretization in time, very standard problem in numerical solving a problem. Yeah. Next one is essentially linked to the first approximation, like core sampling the phase space. To calculate the acceleration, you need to do something, which is actually the most complicated step in any of these type of simulations here. So this is easy. This is the most complicated part here actually that we have to deal with. And one of the simplest approaches to deal with it is called the particle mesh scheme, which actually is quite simple in some sense, I would say, because it it takes as input the particle distribution, so from this first step here, and then tries to basically get like a continuous approximation of the force field or acceleration field. So it's like a continuous field or quasi-continuous field generated through like an n particle distribution. Of course, there are many more methods that you can involve here, but this is like the base model, one of the simplest ones, and actually, I think one of the most elegant ones, I would say, yeah? But because it's very simple. And basically, what you need to do to calculate all the time these kind of accelerations is the following. You need to think about, you need to calculate the force, which is due to a solution of Poisson equation. You see here on the bottom right panel here. And that involves like certain Laplacians of like the Ruđers, and you do this usually on like a uniform mesh. So and the uniform mesh is with respect to like the Eulerian coordinate system, okay, just like a fixed mesh coordinate system. But you could beforehand you calculate the particle positions in Lagrangian coordinates. So you need to find a way to basically swap between the different coordinates back and forth, and this is requires interpolation methods. I will also explain this in a second a bit more what it means. It's a bit technical, but if you want to understand what's happening in simulation, I think this is good to know. So one thing is that actually has been understood.
Sorry, I have another question here. So, so if you go back to your previous slide, so do you assume that the density is constant when you calculate the acceleration?
The density of the distribution of matter, you mean?
Yep.
No, not at all. I mean, the density comes.
So in the Poisson equation, you have a minus grad x of A, which goes like rho. So that rho is, I'm guessing that's the density of the.
Yeah, but rho is the total matter density. So it's really like it's basically relying on the. I mean, there's an approximation. There's an exactness. Rho is like the exact density, and the embodied approach basically assumes that you can approximate this exact density by an n particle density, and this is. In practice, this is really just like a sum of matter particles that are basically in a kind of positioned way with Dirac delta distributions. You have like particles, and there's like Dirac deltas that point where these particles sit.
Okay, so you're assuming. Okay, I see.
Yeah.
Okay, assuming
it's a highly nonlinear problem. The density is not at all uniform. It's the opposite. It's a highly nonlinear problem here. Yeah. So I mean, otherwise you would get completely off accelerations. So acceleration that you need for the kick update. Requires extremely accurate estimates of your local density, and just think you have like a region where you have lots of particles. the acceleration will go crazy, yeah, and this has to be, of course, incorporated accurately, yeah.
Yeah, but so realistically, what is, what's the correct thing to do?
There's no correct way, really. I mean, there's just you need to keep the errors under control. And I showed it in the next slide also what like a few techniques how you can deal with that. Yeah.
Mm-hmm.
So the correct way is basically to keep discreteness errors under control. So I come to this in a second. Yeah. So just one example: spatial discreteness is basically something that is kind of unfortunate, because if you use an n-body simulation, and you want to start the simulations, before you do that, you usually just dump particles somehow on grid positions, like as shown here on this figure here. And you do this very often, like just by placing them at like grid points. But then you actually want to have like initially a homogeneous configuration. Homogeneous meaning like the density is completely uniform. Yeah? But this is not a completely uniform distribution here. It actually is like it has a certain some kind of deformations along the grid axis, okay? And now the problem is the following, that actually followed cosmologists for quite a while, is if you just start your simulation with this configuration and you just give them a little kick, then the particles basically just move a little bit from this initial configuration, and you still see this kind of grid is still imprinted in your system. And this generates like artificial transients that you have really trouble to get rid of. And so we have worked actually on that for quite some time to get rid of this stuff and spare no details. But the easiest solution is just displacing the particles with LPT. This is this analytical approach as far as possible. As far as possible, basically, is just until just before the first shell crossing kicks in. Why? Because you displace particles more, and they lose basically the memory of your initial conditions. So this kind of initial mesh system will completely be forgotten when you have displaced particles sufficiently long enough. Yeah. And the other thing is, this is, goes back to the question of Deepan. What can you do to actually reduce the errors in your computation? Is there are now some techniques that we can use. You see in this figure here on the lower right, like an embody simulation result on the left, where you will just see like coarse-grained particle distributions. And again, this is not really how the universe would look like if you could see dark matter, of course. Yeah? But the image, how it should be, is more like towards the right. So the realization actually is exactly the same in both pictures. But what we did actually is that we found certain techniques that allow us to retrieve from this kind of particle distribution like a very good approximation of a continuous configuration. And this is important. This is not just playing around with like nicer figures, because we want to make sure that the computations to calculate the acceleration is highly accurate. Okay, and for this we need to keep errors under control, and in particular these discrete errors as shown here. So just I think I need to speed up a bit. I'm a bit slow. This is still introduction slides, by the way. But I have not so many core slides. I think the introduction slides are the most important ones today. Just one very interesting like approach how to reduce discreteness is actually using of translation operator that many of you use maybe from quantum mechanics. If you have done work with Schrödinger equations, stuff like that. It's a very similar approach that you start with like a coarse sampled distribution. You just have these kind of red particles sitting here, and then you figure out, okay, the configuration I have locally is not fine enough to give me like a good approximation of the force field. So what you do is you essentially apply this translation operator in Fourier space in two steps. That basically allows you to respawn new particles on the fly, and then you can basically dump the particles exactly at locations by just using this kind of translation operator. So this is a technique that works extremely well on early times when the sheet is still looking very simple, but at later times it's computationally extremely complex, which just points towards the problem that at very late times we don't really have a full understanding how the universe should look in this system here. Another thing is just okay. This is more like almost like a lecture. This part of the slide here is how you basically swap between different basically how you assign mass and relate this to like a density field. So because you want to calculate the Poisson equation, and it's sourced by the density of your particle configuration. And as I said before, basically it involves like swapping between Lagrangian or Eulerian coordinates, the step, because you follow particles in Lagrangian coordinates, and you see this kind of gray lines. Basically, it gives you a default mesh. But what you really want to do is now you compute the density that is forced in the Poisson equation, which is an Eulerian constraint. So somehow you need to find a way to get this uniform mesh onto like a regular grid. And the easiest way to do that, many people are using this for many years already, is called clouded cell interpolation, where basically you just use an interpolating function that basically allows you from the current locations of your particles to give you like an estimator of the density on this grid points. And once you have the estimator on the grid points, it gives you like an approximation of the actual density. You just essentially put this in Fourier space, and this gives you like the Fourier space density, which then you can use as the input to solve the Poisson equation, which of course is usually done also in Fourier space because of this Laplacian here. Now, the cool thing is that we actually figured out just very recently is, well, it exists for many years already in literature, it's called non-uniform Fourier transform. It's actually really a cool trick. The following is, instead of essentially using this interpolation step here, you actually just use another formula that you actually is very well known in the literature. You just use like a relation that the density can be written in terms of the Dirac delta distribution or the integral over it. This is an exact relation for our problem. And when you plug that into the equation 1, you basically get this relationship, which looks, of course, completely different to the equation 1 again. But essentially, it means that you can express the Fourier density without any interpolation step. So, and it's doing this indirectly by using a non-uniform FFT at the end. Yeah? So basically, you just have the particle positions, and directly from that positions, you can perform like a Fourier transform, which makes the problem much more accurate because you don't need to interpolate. Okay, so temporal errors is another source of potential problem in your simulation, but usually it isn't because there are certain stability criteria that you can build in. But it's very important, so this is now coming to the main point of my talk, is this is actually very costly because if you have lots of time steps imply that you calculate a lot of time also the force. And the force computation is the most complicated thing you can do in a simulation. And very easy calculation, if you have more time steps, you have more force calculations. So you want to minimize this as good as possible. And also not just because you need to make this very efficient, this calculation, but you also want to reduce numerical errors. And it's a very classical example. If you have like a numerical solver of anything, you want to minimize the input you give. You want to basically solve the system with as little distortion as possible, because any little operation you add into your problem is a source of another numerical errors. And unfortunately, often numerical errors can accumulate. They don't just get killed away. Yeah? So you want to minimize the operations as good as possible in a good program. And so the question is, how can we essentially reduce the number of time steps of force calculations, or like just having less time steps in the simulation without scrutinizing really the accuracy of your simulation? And yes, it's possible, but you need to do something more clever than just like a standard integrator. So just quickly, an integrator like this is symplectic, which means if you have appropriate choices of these kind of weight functions, gamma 1, 2, 3, you can actually see that it's second order accurate. So it's like globally preserves energy to second order accuracy. This is quite good already. It's also symplectic, which is nice. It has some certain built-in energy or like other conservation laws imprinted. But what it does not have the right asymptotics. So if you basically want to evaluate with this integrator, like close to times of Big Bang, you basically go from the time bottom down to the Big Bang, the momentum blows up. And why? Because in a symplectic integrating scheme, the P here is canonically conjugated to your coordinate. And unfortunately, it comes with a 1/a squared here in the Hamiltonian that basically tells you that the momentum blows up. It's basically a property of like phase-space conservation. It's really essential problem of using Liouville theorem at the Big Bang time. So it doesn't have the right asymptotics, at least as we understand it. And it's also, it doesn't have the built-in properties that we have gained actually from perturbation theory. So this is the important bottom line of this talk, I would say. And essentially, because of these two not satisfied properties, it also does not scale well if you reduce the number of time steps. If you just agnostically reduce your time step in a standard integrating scheme, you get completely bullshit, basically. So what else you can do is the following. There are like certain new integrator methods. They actually have been invented for almost 10 years now. So it's not completely new, but it has been under development the last few years. They're called a D-type integrator. So in a few slides before, I showed you that in Lagrange perturbation theory, you can essentially get highly accurate solutions, at least at early times, when you expand around this D-time. D-time is essentially just like a strength of your how strong like a linear fluctuation in your density field is evolving in time. When it turns out, when you formulate your integrating scheme with respect to this different time variable, then the integrator looks almost similar, only now that you don't use like a canonical conjugated momentum, you use like a velocity variable that is related to the coordinate in this way. This is a non-canonical relationship here. It turns out when you do simulations in this way, you have all the other boxes ticked. You have like the built-in properties that we know from perturbation theory early times. And it's also because of that is highly performant for a few time steps. So really just like changing essentially the integrating variables from here to here, it looks trivial, is a major simplification of the problem.
Is D a linear growth function?
Yeah. Just to understand growth functions.
Can I ask another question here? So how do you make sure this is Lorentz invariant? Because you're technically, I mean, you're not taking the A going to zero limit, right? So if you put a regulator, I don't know if this is equivalent to putting in a regulator or something. So aren't you breaking Lorentz invariance in some sense when you're evolving the whole thing?
So first of all, what we're doing here is fully Newtonian. So I mean, we don't have to deal with
fine.
any.
So this is all Newtonian. Okay. Absolutely. Then it's absolutely.
But there is a direct correspondence to the full GR manifold, at least in the weak field limit. So what we do is we have a one-to-one correspondence in the sense of weak field formulation of GR.
Okay.
So so I mean, correct A to zero asymptotics is not really relates to like a physical problem. It's more like a mathematical problem. Because when you want to initialize the simulations, I mean, maybe in a naive way, you think, okay, you have Big Bang, then you have all the phase transitions in the early phase of the universe, and you have CB, and well, now we have this our simulations that we want to start. You would call this a forward approach. But in practice, what you do actually in this kind of simulation setup, you do something different. You actually use a linear Einstein-Boltzmann-solver, it's a technical thing, and you go up to today's time, and then you rescale essentially the initial conditions appropriately that you can start a new universe that starts actually the Big Bang. So when you do like an LPT initialization, this is what you do basically. So basically, when I say the correct asymptotics for A going to zero, it means that we basically swap a different problem from like early universe physics to late time physics. And the easiest way to deal with that is by incorporating this knowledge in your integrating scheme. But you don't need to do that. I mean, you can also avoid that problem if you want to.
Okay, I digress, but I'll ask you a question later, maybe.
Yeah. Yeah. So short story. It's a mathematical subtlety, basically, not physical reality. Yeah. So there are actually a couple of integrators. They are already following this kind of road. And one of the first ones, actually, this involves also Uroš that we talked about today, is FastPM, and it basically is using like a drift team that is using at each time step like a 1 LPT correspondence. So if you do like an perturbative analysis, you can show that at each time step they do essentially just what we can do at linear perturbation theory. And the last 2 years, actually, my colleagues and myself, we made some progress in these other integrators that are basically doing something quite a bit better. And I show you in 2 slides basically how much better. And then I need to stop anyway soon. Yeah. So I will just quickly show you this new integrator that is published or we submitted in probably 1 or 2 weeks or so. It's just finishing up here right now. And the idea is the following. So you see in this kind of sketch here on the right-hand side, like the typical routine of like an integrating scheme. Yeah? So you have like in a drift sense, you have like one time step, and the drifts are in a numerical sense, they're always like in a linear fashion. So you really just like drift the particles like in a linear way. And that basically means if the exact trajectory is curved, which of course is the practice, you will get basically to a point somewhere where the kick is calculated at the wrong location. And basically we found a way to auto-correct this on the fly, basically to calculate the wrong force update in this location that pulls you back basically on the trajectory. So it's quite a cool trick that basically we just use Einstein's grid principle to calculate the correct solution. And when we do that, we can actually push particles back on this kind of trajectory that we know is the right one. And just like two slides or so about performance, and then I'm finishing. So this is just showing like this three new integrating schemes. All of them are actually highly performant, even the one from like 8 years ago or so, the fast PM. So, and I'm just as a performance test, I show you here basically like a three-fold calculation. You basically just drift particles, and you give like 3 times like an update on the force field. Okay, you start at the Big Bang here at Z infinity, that is just redshift, and go to like early times, and then you calculate the first time like the force field, and then you do another step, and another step, another. And you want to see that the residual that is shown here with regards to the exact solution is going smaller and smaller. And you see that these new integrators, fast PM is really doing a good job, but these 2 new integrators doing a far better job because the residual is basically just getting wide, which means it's basically converging towards the correct solution. So although our integrator is just all upgrade to second order in perturbation theory, when we repeat time steps, we actually get higher order conversions. So this is the first time where we have basically like a one-to-one correspondence between like high order perturbation theory and like a simulation scheme here. And just a bit more like on the level of summary statistics, what the performance is. It's quite small. I hope you can see it. So this is just like an example that we want to later apply to like effective fluid descriptions. Effective in the sense like you guys also use it in particle physics. We basically want to include some other physics that happens in our case, on very small spatial scales. And to do that, we basically want to work with like a certain effective fluid. So it's in the present case, we do this by applying a low-pass filter in the initial conditions. Never mind. So it just basically gives you like a smoothed fluid, and we want to simulate this as well. This is just a nice test, basically, what the integrators and also perturbation theory can achieve, because in these regimes, perturbation theory is still almost still meaningful, but not completely, whereas integrators are slowly gaining winning over, because we enter into a regime that only simulations can handle, basically, after shell crossing. And what you see is that the new integrator and also PowerFrog are by far the best. So they have like sub % precision. Here, for example, the dotted line here is basically our bullfrog shown here. For this kind of filter here, you need only one single time step to get like % level prediction in the power spectrum. So it's really just, you essentially initialize your problem from Big Bang up to this redshift, which is today. And you just need a one time step. And as a comparison, I show here like in dashed lines the accuracy, freedom to accuracy to like the reference simulation that you did just a standard symplectic integrating scheme, and you needed like 200 steps, 400 steps, 400 steps to get to this level. So basically, by just changing the integrator, you went down from like a few order of time steps, like 2, 3, 4, from initially 400 time steps. So it's much more efficient. So it's a big improvement, especially on these large scales that we're mostly interested in. And okay, I think I will skip this. This is just more like for the people who know only Coda. There's an integrator that is somewhat similar, but not really. So it's there's some differences. It doesn't have the right conversion, not the good performance that we see in our new integrator, but it's also nonetheless quite good. But it depends on some hyperparameters that need to adjust. So we don't have any hyperparameters in our program. It's just all is fixed in the integrating scheme. We don't do any fudging. Okay, I'm a bit over time, so I will stop here with the conclusions and take some questions here.
Questions? On the floor and online?
More of Japan, yeah.
Sorry, I bugged you too much, maybe. Sorry.
No. Not at all. I think questions are very helpful, because it gives feedback. So I know.
Bruce has a question. Bruce has a question.
Okay, sure. Yeah.
Hi. So first of all, thanks for the talk. Extremely informative. Can you go back to the slide where you discussed the role of grids and discretization and so forth?
This one here?
No, before that, where you've okay, here. So clearly I see the problem that is introduced by starting with particles on a grid, because I mean this doesn't reflect the full symmetry, it imprints a certain structure, and when it's collisionless, I can see that can produce really dramatic problems. I'm afraid the solution went by too quickly for me. Can you explain this, how the solution works again?
So, okay, so what I'm showing here on the top right sketch is essentially you start with a completely like a lattice configuration with your particles.
Yep.
And you essentially this kind of first movement where the particles just slightly deviate from this grid configuration. This is what we call essentially providing initial conditions for simulations. Because normally you would not like start directly the simulation on this grid configuration. The step is more like called pre-initial condition. So we really just like dumping particles, because at some point you need to put particles before you just press switch like start. And so this first little displacement is what you normally do in this Lagrangian perturbation theory. So you basically use Lagrangian perturbation theory input to give the initial displacement of particles for like a short time, and also the velocity of particles. And then this is provided to the simulation code, and then the simulation starts basically. But the problem is the following: if the initialization step takes too little time, then the initial conditions still have imprinted this lattice configuration.
Sure.
Okay? And the whole point basically of I think there are 3 papers on this, or maybe even more, including also papers from Harvard, is to forward the particles in this initial step as much as possible, so that you lose this memory of your initial configuration, because it's an artifact that you don't want to have in your system.
Yeah, so I still don't understand how you get rid of it, because I mean I can see with that displacement that you've shown.
Okay.
I can see that it's a grid.
The
system must be able to see that it's a grid, and so I don't understand how you fixed it.
So I fixed it by really just like initializing the system longer. So I'm showing here like a sketch where I just did a tiny displacement, and I did not show you like a figure where I have a large displacement, because Keynote didn't want to show me this properly here. So it was probably too complex, this simulation with Keynote. But yeah, if I just basically do this displacement, what I showed you in this initial stage, with a much larger time step, you would completely lose this kind of initial memory. So it's hard to see maybe in this figure here, but basically if you just try to extrapolate, the particles move further away from the initial grid locations, and you really lose the memory. You don't see it anymore in your particle configuration at late times. But
okay, so you don't truly initialize until you've been able to lose.
Yes, exactly.
You've been able. Okay.
This is like the one way to deal with the problem. So basically, if the whole universe has like a timeline of 13 billion years, you literally use like perturbation theory to first displace particles from time 0 up to redshift about 15, which is, what is this? Maybe 10 billion years after the Big Bang. So the first 10 billion years or so, you basically just use like this perturbation theory recipe, and then you use this as the input for your simulations. Or you actually can use.
That's more clear. I was misled by the figure.
Yeah. Or this is like an alternative, basically, because now we have simulation techniques that can deal with these grid configuration. Is precisely using like numerical approaches that remove this discreteness errors, because this is a discreteness error effect. This kind of initial lattice configuration is a discreteness effect to some extent. And we do this by using, for example, this Fourier interpolation techniques, or like just more accurate mass assignment techniques. Because when you do that, you essentially you do not really like worry too much about the particles that you're tracing right now in simulation, but you're just spawning as many particles as you need, so that you don't see this lattice anymore in this fine grid.
Is it too naive to just drop the particles using quasi-Monte Carlo or something like that, so there's no lattice to begin with?
This technique exists. It's called like class initial conditions, but it has similar problems. So it's
Okay.
It's a different initial condition generator, but it's not really used anymore these days because it has other problems. I mean, there are people using it, but it has not really like an advantage, unfortunately. Yeah? So the best is really just, and I think the easiest, if you don't want to use any kind of sophisticated discreteness suppression schemes, you would just initialize your simulations using LPT up to late times, because it's actually also extremely cheap. It's much cheaper to use federation theory in this initial billions of years than using simulation. Yeah?
Yeah, no, that's clear. Thank you.
Any other question? I have one. With the particle mesh, gravity solver, and your Fourier technique and the FFT, doesn't like standard FFT assume that you have nice regular spacing of the grid?
Yes, yeah.
So how are you now? You have this non-grid grid.
Yeah. So I mean, this is it's very hard to visualize. I think I tried quite long to make this visually precise, but it's still a sketch. Okay. So the idea is that this Poisson equation is restricted to like a fixed coordinate system, like a regular mesh. Yeah. Okay. So what you really want, if you want to use FFT, like fast Fourier transforms, yeah. what you need is like a good estimate of the density on these grid points, because this is exactly where your FFT will be evaluated. Okay, but because you're doing like a mix between Lagrange and Eulerian schemes, you need to find a way to basically get good approximations as good as possible on grid positions. And when you do that, you basically need to use these interpolation steps. And this is one of the key techniques that
Cloud and Cell, right?
Cloud and Cell, yeah. You can also use higher mass assignment like TSC and what else. But this is also, it's just doing this a bit more sophisticated. So this is like there's like the nearest grid point approximation, which really would basically do the following trick. It's basically, well, there's a particle sitting here in this one corner. I would just give the whole mass to this grid point here. This is like the nearest grid point approximation, which is extremely crude. And the CIC is like the next to leading order correction, which basically has like more like an interpolation kernel that assigns not just the whole mass of the nearest particle to this point, but also a little bit to the other points. Yeah? And then of higher order mass regimes. Yeah? Now, so again, the whole point of this interpolation step in this figure here is, how can I get good assignments of the density of your particles to grid points, so that I can calculate the Poisson equation accurately? And the cool new trick is that it's actually also used in other fields, not just in our case. But the way I understand it is basically essentially finding a way to, instead of calculating interpolated density in Eulerian coordinates, you essentially just use another trick that allows you to essentially skip this interpolation step at all, because now you don't need to interpolate to these grid points anymore. What you do have now, you have like a non-uniform mesh in Lagrange coordinates, and you just ignore that. Or you don't worry too much about it. You keep the Fourier space uniform, so the Fourier space coordinate here, the k here and the k there, is reflected to the Eulerian coordinate. So it's conjugated of the Eulerian coordinate.
So
but the mesh
you're smoothing onto a funny grid, but you're still doing your FFT on a regular grid?
Yes, but there's no interpolation involved anymore. It's really just taking as the input the current particle positions in your non-uniform mesh.
And does it introduce an error?
It is much more accurate. It actually is completely skipping essentially the interpolation step. Interpolation means approximation. So it's much more accurate.
So your FFT is not on the funny grid.
So there's still an approximation because you're doing FFT, and FFT is intrinsically not accurate. Yeah. There's always approximations involved, but it's much more accurate than doing this in this above.
What about a tree code or something like that?
Okay, this is just like particle mesh idea. If you do a tree code, it's much more complicated. I mean, you do like a complete like tree calculation. You try to group particles in the right way. there's a multiple methods, there's a lot of other stuff you can do.
Yeah.
But we actually also tested in this paper with Florian and Oliver, that one, can give reference, also a tree method. And it points out, I can also show you a figure, that the most accurate approach that we found, there's a couple of things you can combine, like different techniques. The best approach, condensed approach, is using this sheet interpolation and the non-uniform Fourier transform. And if you do instead, we have the figure here in a second. You can also do a tree code. We implemented that as well, but it's not as accurate. So the tree code has other features, but it's not always the best. For large scales, it's not very good. Let's see where it is. So, yeah, so this figure here. So we compared basically like residual errors, and we tried a couple of different schemes. Yeah. So here, the dark green line is 3 p.m. And you see, I mean, the error ideally has to go down. If the error goes down, it's we have achievement with higher order achievement with perturbation theory at these early times. And you see just 3 p.m. and it's not really reducing the error. So there's like a limitation to that, although it's like one of the more sophisticated ways how to calculate the force field. But if you do instead like the sheet interpolation, what we do, plus this non-uniform FFT, you get this, what is this color called? Cyan color, yeah, these stars. It's going down. You can achieve like the same precision with other techniques. That basically is just like all the other techniques here on this side here. Or you just use the resampling. So this sheet interpolation from the keynote slide plus the non-uniform FFT here. This gives you the best accuracy here. Yeah. Much more accurate than 3 p.m. or CIC, anything like that. Yeah. Okay.
Anyone else? I don't know.
Yeah.
With your leapfrog, isn't the canonical momentum just the non-restrictive momentum?
Sorry,
like what do you usually call Q? Like if x is a comoving coordinate,
yeah.
P is just the non-restrictive momentum, right? That's the momentum that's canonical to comoving.
Okay, the momentum canonically to x, I think
Q, right?
in EDS universe is a3 times x dot, and dot is just the temporal.
I thought was always Q times AP. I thought always it was Q. Maybe I'm wrong.
Q, you mean like Lagrangian coordinate?
Not the Lagrangian coordinate, like just your physical momentum times A.
No, it has a scale factor in it, in a way that the momentum really goes
no, it's bananas. That plus whatever gravitational.
Yeah. No. So here, this is really the momentum here. If you can of course use any kind of integrators, and you want to calculate this at early times, but nobody was doing that because the system will completely go bananas. But because the momentum goes to infinity, when t goes to 0 or a goes to 0, this guy goes completely crazy. Huh? Why? Because
that's why I was surprised about
because P really has internally like a scale factor implemented, like 1/a something. I think power to the 3/2 or so, and that goes to infinity. The whole thing. When a goes to 0.
Yeah. I had a comment here, which I don't know if this is right. So the a going to 0 limit is not really physical here, right? Because you're in a regime where the a going to 0 limit doesn't really make sense. Right?
Yeah, it's really just like exploiting, it's a mathematical property basically that is makes modeling very easy. So it has physical consequences, but in practice we don't really want to have like a simulation at the Big Bang. We really just want to use.
Yeah, so you always need to put a so if you really wanted to extrapolate it there, I mean, you always need a physical regulator or something, right? I mean, because otherwise, I mean, the physics has changed, right, in some sense.
The physics has changed, but again, this goes back to like it's called boundary layer problem. So basically, it's just hard to summarize the problem on mathematical level. But it's the following: if you have like different stages, you go the universe through. I mean, you have inflationary phase, then you have a phase transition, you have like reheating, then you have all the other phase transitions of the universe, then CMB times, and all these different stages, the different phases of the universe, come with a different physical description. Which means for each of the stages, you have also different equations right?
Correct. Yeah.
So now you need to find a way to swap from one set of equations to another one, and to another one, and to another one.
Yep.
And this is a problem that people have worked on for decades to make this in a concise way. Okay, and there are a couple of ways how to deal with this system. And the easiest way is the following: is basically really just to start your embodied simulation, like literally at the Big Bang, with somewhat a fake universe. A fake universe in the sense that if you go on ultra large cosmic scales, that the power spectrum has the correct behavior if you look at today's observations. You basically make a matching how on ultra large scales the power spectrum of matter needs to look, basically, and use this as the input to match like a fictitious universe, and that you basically start to initialize again at the Big Bang. This is what is, again, this is just, it's a simplification of a very complex mathematical problem. What you could do instead is you do it really like the hard way, is really you have your equations from A to B, equations from B to C, and so on, and then you swap basically within a so-called boundary layer. Boundary layer just means that you have like a certain temporal regime where you basically need to get on the bus. There's a bus stop basically. I need to go from one description to the other one. Okay, and when you do this, then you need to basically model the whole system in a forward approach, and that has unfortunately a lot of disadvantages. For example, I talked today not about radiation, but of course radiation still plays a role in our universe. We of course see still like incoming light rays from everywhere. So it's a small fraction. Or also if you care, for example, about neutrinos, which we do actually also care, sometimes there are different descriptions that are better to deal with neutrinos. Yeah. So, but then what it means is that you need to incorporate the physics from radiation and from, in particular, from neutrinos on the fly as well. Whereas in our approach that we, what I just showed you here, and that's not our approach, the main approach that most people use, you can kind of exclude that in a way, and then incorporate it later again by using perturbation theory. So it's kind of a trick that basically boils down a very complex problem into like a Wolf problem. And for this, we need to generate kind of a fictitious universe. And once we have that and we can simulate it, we can include all the most of the physics that we actually exclude by perturbation theory. I say most because we, for example, cannot do this for baryons, which is very complicated. But for neutrinos, and to some extent also dark energy perturbations, we could include like that. Yeah. So it's just a trick that works for like the vanilla flavored universe very nicely. But as soon as you want to go like on very small scales, for example, where you care about baryons meaning like visible matter, yeah, then you need to do something more clever than just this kind of initialization at Big Bang time. So then you need to do something much more sophisticated. Yeah.
Right. Yeah. I mean, also, I mean, in some, so this is still a Newtonian description, right? I mean, using Newtonian approximations. I mean, at some point, that approximation will also break down at early times, right? So you probably...
Yeah, definitely, yeah. So again, I mean, actually, this, I'm happy that you asked these questions because I've worked on this stuff for, I think, maybe 5 years, 6 years in total, I say, yeah. So this is exactly how you can do like a simulation in a Newtonian universe and relate this to like a full GR description. I spent years understanding how this works, and it's just hard to summarize this year's work in a few words, but it works. Yeah? As long as we are in a weak field regime, which means that you are in general relativity, and your metric is at all assumed at all locations to be in a weak field sense. Weak field meaning that you don't you're not close to like black holes and such things. Then you are in a weak field regime where the potential, the metric fluctuations are sufficiently small. And that regime is fully nonlinear in the Newtonian sense, but also in the GR sense. And we have an exact understanding how this kind of weak field GR formulation looks like in the Newtonian and the other way around. So even including neutrinos, for example, we can do this in a rigorous way. Yep. We just need to assume that we are far away from black holes because that's too complicated.
Yeah. Okay, all right, thanks. Yep.
Another question from the floor or from online? Well, let's close this at least formally anyway.